So, moving on now to looking at a couple of things that might change K, okay, or things that we perhaps might think would change the value of K. Okay, we're going to look at this system. It was the first one from the previous slide, nitrogen and hydrogen turning into ammonia. Here's the equilibrium constant expression. Okay, and let's look at something that maybe might change the value of K. Okay, we've been looking at things like adding and removing reactants or products. So let's say we put some more hydrogen in here. What would happen to the value of K? Well, this value would increase. But Le Chatelier's principle tells us that if we increase this, that the system will try to lower it. And it will do that by reacting these two things together to make more of this. So, although the initial change means that Kc will get smaller, okay, because H2 got bigger, as the system responds and returns to a new equilibrium, the concentration of ammonia will increase, the concentration of nitrogen will fall, as will the concentration of hydrogen, but not beyond its original value. Okay, and so Kc will actually start to grow again. And in fact, K, or Kc, the equilibrium constant, will not be affected by changes in concentration. Okay? Because Le Chatelier's principle says that the system will establish a new equilibrium where K will return to its original value. Okay? So the equilibrium constant is a constant. Okay? And there's only one thing that will affect it, and that is temperature. Okay? Well, let's just look at another example. That's a very important thing I just said there, by the way, that I kind of just slipped it in at the end of the slide, really. K will only change when the temperature changes, okay? Otherwise, it is a constant. Okay, so let's look at this equilibrium system where we've got, again, calcium carbonate decomposing, turning into calcium oxide and carbon dioxide. Okay, Kc, in this case, is equal to the concentration of carbon dioxide because it's the only gas, or AQ, in the expression. Okay, and you might be thinking, well, what about here? I mean, Le Chatelier's principle says that if I increase the amount of calcium carbonate, then Le Chatelier's principle says that this system's got to lower it. So I'll produce more CO2, and that can only cause K to increase, right? Well, yes, but we've missed something quite important there, because although we've added more calcium carbonate to the system, we haven't caused its concentration to change. Okay, so in other words, adding more of this solid, there'll still be the same number of moles of solid in every litre of solid, right? Because it's a pure solid, so its concentration is constant. Okay, so in other words, by adding more of it, I haven't changed the concentration. So Le Chatelier's principle, which says that if I increase the concentration, the system will try and lower it, Le Chatelier's principle says that nothing's going to happen here because I haven't changed any concentrations. So K will remain the same if I add more calcium carbonate. However, this reaction here is endothermic, okay, whereas this one is exothermic. So if I heat this reaction up, Le Chatelier's principle says that it will try to cool itself down. How will it do that? It will favour the forward reaction. That will produce more products, okay, which means that the concentration of carbon dioxide will increase. So for this particular reaction, if I increase the temperature, the value of the equilibrium constant increases. Okay? If I decrease the temperature, the value of the equilibrium constant would decrease because the concentration of carbon dioxide would fall as the system tried to heat itself up. I'm just going to go back to the previous slide and have a look at some temperature effects here. Okay? In this example, the forward reaction is exothermic and the reverse reaction is endothermic. If I cool this reaction down, it will try to heat itself up. We'll get more products, less reactants, and so this equilibrium constant value will increase because the top of the fraction will grow and the bottom of the fraction will fall. If I if I heat this reaction up, the endothermic reaction is favoured. Okay, should remember this from our temperature principles film in the past. Okay, so the endothermic reaction will be favoured. We'll get more reactants and less products at equilibrium, and so the value of Kc will fall. Okay, so the equilibrium constant can be affected by temperature, but not by any other change in conditions. That's a really important thing about K. So you should know by now how to write an equilibrium constant expression by looking at an equation. You should know what things will affect the value of K and what things won't. And also you should not worry about ever trying to plug some values into this, because in a WACE exam you don't have to calculate the value of K, but you do have to be able to say something about the position of equilibrium based on the size of K. So if K is a very small number, it tells you you've got lots of reactants and not very many products. If it's a big number, i.e. bigger than 1, right, because the top of the fraction is bigger than the bottom, then you've got more products than you have reactants.